Hey, yo, what's up, guys? Baby Bear 4812 coming at you one more time. First off, forgive me for my ridiculous looking ensemble. It's freezing today. The heat isn't on in the building, and yeah, that explains the sexy look. But heat or no heat, we got questions to answer. And today's question is 1300, so it's one of the newer ones. And it's the sum of mutated array closest to target. Now, the question is, I think it's a bit unique. I haven't really stumbled across many that were like this. And it tells us that we're given an integer array r and a target value called target. And we need to return an integer value such that when we change all the integers larger than value in the given array to be equal to value, then the sum of the array gets as close as possible to the target. Okay, so it's a bit of a mouthful, but so we'll kind of walk through what this actually means. It says in case of a tie, we return the minimum such integer. And what I'd argue is the hardest part of this question is to notice that the answer is not necessarily a number from the array itself. And we'll see that they don't really give a good example of that here, but we'll walk through an example and see where that happens. So imagine we're given this input array here, and the target is 10. The output we would return is 3. And again, we'll talk about how we're going to get this, but the reason we're returning 3 is because when using 3, the array converts to 3, 3, 3, which sums to 9, and that's the optimal answer. The reason it becomes 3, 3, 3 is because if the value we're outputting is 3, we're saying take every number in this array that's greater than 3 and bring it down to 3. So 4 becomes 3, 9 becomes 3, 3 stays as it is, so we get 3, 3, 3. That would sum up to 9, which is as close to 10 as we can possibly get in this question. If we tried something like 4, for example, we'd have 4 would stay as it is, the 9 would become 4, the 3 would remain as it is, we wouldn't change it, so we'd have 4, 4, 3, because 3 is less than 4, and that would sum to 11. Since we're told here that in the case of a tie we return the minimum of the two integers, that's why we would return 3 in this case instead of 4. Even though 11 and 9 are the same absolute distance from 10, we are choosing the smaller integer, hence 3. In this problem here, in the second example, we've got 2, 3, and 5, so this one's kind of in increasing order. As you notice here, this one was not. We said that the output is 5 here, and the reason the output would be 5 is to think about the following. Well, how do I put it? Let's put it this way. If we're outputting 5 and we notice that 5 is already the largest number in this array, none of these numbers will actually be changed. We can actually see here that 2 plus 3 plus 5 already equals 10. So the sum of the array is the target. And so when we're outputting 5, really we're saying don't change anything in this array. An equivalent statement could have been return 10 or return 50 or return 100, because remember, we said whatever we're returning, we're going to take all the values in the array greater than that number and reduce them to that. There are no numbers greater than 5. There are no numbers greater than 6 or 10 or 50 or any of the numbers that I mentioned. The reason we're returning 5, though, is because it is the smallest of all those possibilities. In this array, so we're not going to go through the math here on how this one checks out, but the target is 56,803, and the output, notice, is 11,361. None of these numbers is 11,361. What we notice, though, is that if 11,361 is smaller than all these numbers. And if we were to, that means that by replacing this, we're implying that we need to change every single one of these numbers to 11,361. Summing that up would get us as close to 56,803 as possible. So I hope that at least the question makes sense now. I don't think the answer is obvious, and we'll obviously walk through how to get to these numbers. But that's what the question is asking. Now, we look at a few of these examples here, so I've copied them over, and I think one thing that needs to be addressed right off the bat here is if we're looking for all the numbers that are greater than a certain value we have right now, the intuitive first step to take would be to sort this array. We're not concerned about the order of these numbers, so we're not concerned about if they're numbers larger than value that come before or after a certain index. We just want all the ones that are larger or smaller than a value. If that did matter, then this would be a whole lot more complex, because maybe then we'd have to think about like what the longest increasing subsequence would be, or one of those kind of related problems that I'd argue are harder and would definitely make this a really tough problem. But since we don't have to worry about any of that, we can go ahead and say let's go ahead and sort this array. So maybe instead of thinking about this one, we'll sort it to become 3, 4, 9, meaning that no matter what we do from here on in, our minimum time complexity will be O of n log n. Okay, so that's going to be something to keep in mind as we go. Now, how do we even begin to think about this question? Well, okay, we have it in sorted order. I would then argue the following. Since it's in sorted order, we can almost walk through it increasingly, and maybe every step along the way we'd make some sort of decision or see like what happens if I change all the numbers from here on out. So if I change this 3, or maybe I return and say, hey, 3 is my answer, everything here is going to be changed, right? If I change something here, then everything after the 4 is going to be changed. If I'm looking at this, longer example over here, if I not change, so but maybe I say 5 is my answer, 12 is my answer, I know that everything after this will become a 12, or everything after this will become a 5 or a 4 or whatever number we end up choosing. So if we think about walking through this sequentially, really the question we're asking ourselves every single time is, what number would I really want right now? Okay, what number would I really want right now? And so I would think about the following. If we know that we need to get to 10, if I know I need to get to 10 and I'm sitting pretty here at the beginning of my array, and I know I need to get to 10. In an ideal world, if I could have my pick of the litter, what number would I want this number to be and all the rest of them to be? So if I've got 3 elements here and I want to get to 10, and I want all of these 3 elements to sum up to 10, in an ideal world, I want each of these numbers to be 3.33 yada. I know these aren't integers, but if we just think about doing the division, really, I want to have my target divided by my length. And if I could have that number, that would be awesome, because I could literally divide it, and I know that from wherever I'm sitting, the length of kind of what's left, if we were to take the target we need, divide it by that length, we'd get exactly what we want. Problem is we can't return integers, or sorry, we can't return decimals here. We're working with integers. So what I'm going to do is that every step along the way, I'm going to say, I'm interested in the target that I have, and divided by the length, and I'm going to round that number. Well, if we round 3.33, we do actually get 3, and we notice we're already sitting on this 3 right over here. So what we're saying is, to get to my ideal answer, as close as possible to it, I need to change all the numbers from here on out to be 3, right? And it just so happens that this already equals 3. That number that we want is in the array, and so that's how we're going to get there. Okay. This first example, though, I think these examples are a bit weak, because I don't think they fully kind of illustrate the thought process. So if this one didn't paint the picture fully, I promise through the next three it'll make a bit more sense, because there is a bit more complexity to it than that. Let's pretend now that I'm walking through this array. This one here is sorted. I'm sitting at this 2, right? I'm sitting pretty, like I said, and the first thing I ask myself is, well, I want to get to 10. Okay, I want to get to 10, and I know that from here, I've got a total length of 3 ahead of me. In an ideal world, I want all these numbers to be 3.333, right? So by rounding, I'd want them to be 3. Okay, if I want all these numbers to be 3, problem is I can't change this number to a 3. It's going to be a 2, right? Because 2 is smaller than 3, I can't change it. If we had something like 6, 7, and 8 were my 3 numbers, and I knew that from here I wanted all my numbers to be 3, easy. I return 3, because all of these, since they're all increasing, or at least they're level, they're either level or increasing, they would all have to change to a 3. But that's not what happens here. So maybe what I can do is I can track something like my number needed at any given step of the way. Okay, my number needed in this case would have been 3. However, I'm not sure I can do much with that, because I can't change this number here, so I don't really think this will give us the answer. I'm walking through the thought process here. We'll formalize this in a moment, but that's kind of where we're thinking so far. All right, what if I take a next step over now? I'm going to start looking at this second index here. Well, if I'm looking at this number here, and I want my sum to be as close to 10 as possible, I need to acknowledge the fact that whatever has happened behind me is now invariant. I can't go backwards and change things. If I change, this number, and maybe I notice 3 is my answer, and I want all the numbers greater than 3 to become a 3, this number is going to be unaffected, because we originally sorted it. Everything behind me is fixed. I can't do anything about it. These numbers before me are already going to be part of the sum that I want. This 2 is going to be part of the sum that we're using to get toward the target. So what I need to do then, as I'm tracking this, is to keep track of the sum that I've had of all the numbers so far that are not changing. So far, I've had a sum of 2. This sum of 2 will stay here no matter what. Whatever I choose to do from here on out, all good. But we need to take into account the fact that we've already taken 2 off of our target and our total sum. What does that mean for us? That means that now I've got 2 possible numbers I can change. Now, do I want these 2 numbers that I have left to add up to 10? Well, not necessarily. I need to get them as close as possible to 8. The reason I need to get them as close as possible to 8 is because I want 10. I already have 2, so I need to get 8 from these 2 numbers. What does that mean? That means I'm interested in finding my target minus my sum so far, right? So sum so far, which again is 2 for now. And now what am I dividing that by? Well, I want 8 to be, split up among whatever is left. And so that, in essence, is equal to the length of what I've got, this entire array, minus where I'm sitting. Right now I'm sitting at index 1. So minus index 3, the length of this, minus 1 gives me 2. I'm interested in finding the total sum minus whatever I've seen divided by whatever's left. And whatever's left is this total of 2 units. So this right over here, and of course rounded again like we did before because we need to return integers, is going to be the logic behind how we're determining what number we need from here on in. If I was to change all my numbers from here on out, what number would I want? Well, in this case, our target is 10 and our sum so far is 2. That gives us 8. My length minus my index, so however many units are left, that's 2, would give me 4. Okay, that means I want to get 4. Now, could I change this number to a 4? No, unfortunately I can't because it's smaller than the 4. So I keep going. I keep going, and again, this will become more clear when we go to the next example, but I keep going, and I acknowledge that, okay, well, so I can't change anything here, but I have now seen the 3. The 3 is now invariant. I'm going to add this 3 to my trailing sum, and I'm going to have a total of 5. Okay? I'm taking my next step over now. What number do I need from here on out to make the magic happen? Well, my sum so far has been 5, and my target is 10, so I need 5 more. Over, how many units can I change to become a 5? Potentially, if they're all, greater than 5. Well, my length is 3, my index is 2, so I only have 1 unit left here. 5 over 1 is 5, meaning that the number I need is 5. Oh wait, well, we are 5, we're looking at the 5. Meaning perfect, we've found the number we needed, and it's equal to the number we're looking at right now. Awesome, we're returning 5. So once we see it, we return 5, and that's it. And that's how we'd solve this one over here. Now, I think one of the harder parts in this question is if we can kind of acknowledge, like, I think this formula makes sense. I think, at least for me, what I struggled to wrap my head around the first time is how do I decide when to stop? Like, when have I found that number that I need? And it's got some sort of relation to the number I'm looking at here. So we saw that the 3 and the 2 are somehow related. Like, we weren't too happy about the fact that we needed more than we had at the moment. Then we had the same issue with the 4 and the 3. And then finally, in this case, we said, okay, well, we need a 5, and I have a 5, so cool, let's return it. But what if we had this case where the number we want isn't in the array? So what we need to think about it is what I'll call our exit condition. Is, again, I think we've determined this relationship. This one ain't the hardest thing to figure out. I think this one is, not easy to see the first time you look at this problem, but I think it's digestible. The part that's left that I really want to formalize is going to be, how do we determine our relationship between the number we need and the number we have so far? When do I say, okay, I'm done, I found my best possible answer, and I'm going to return it? I've drawn out a bit of an extended or a longer example here, which we'll walk through relatively quickly, but I hope that by walking through this example, we'll answer that question on when have we found the number we want to exit at. So we've kind of determined what we might need to do is we're going to need to keep some sort of sum, our sum so far, and I'll keep a track of also the number we need at any given point. And so this total array's got a length of 3, 4, 5, 6, 7. So I'll say length equals 7, and I'll keep that up here. And I've written this example out on paper just so I can skip doing some of the math and wasting time there. Let's say we were to start this example, from scratch. If I had my target was 100, and my first number, well, forget even the first number for a second. If I could ideally, pick a number from which I could set this entire array to in order to get 100, that number would be, after rounding it, it would be 15, right? 15 times 7 would give us, 95, and that would be the closest that we can get. If all of these numbers, hypothetically, if this 2 was a 22, and this was a 23, and this was a 25, and we kept increasing, then I could just realize that, well, I can change all these numbers to 15. The reason I can change them all to 15 is because they're all bigger than 15, okay? So that should tell us something. If number needed, maybe number needed is less than, or I'm also going to say equal to, because we saw equal to in the previous example, the number we're looking at, or maybe a at I, return num needed. And that's going to be the logic. This is really the formal logic of what our exit condition is going to be. I acknowledge here that if I could set all these to 15, we'd be happy campers. That's the best I could do. Can I change it to 15? Can I change all of them to 15, I should say? I cannot. Why can I not do it? Because we know there's at least one number right here that would not become a 15. I don't know what's going to happen with the rest of these. I haven't checked them yet. You know, maybe this is 32. Maybe this would become 15. And maybe all of these would become 15. But we don't know that yet. All I can say is whether or not this one for sure can become a 15. It cannot. So we could keep going and searching for a more ideal answer. We acknowledge that we've seen this number. So we keep a trailing sum, and that's 2. And finally, we move on with our lives. Next. From here on out, we notice that we now need to get a target of 98, 100 minus this 2. To get to 98, we need to change. We have 6 units that we can work with. 98 over 6, and again rounded here, would give us 16. However, 16 is larger than this number here. I can't change all these numbers to 16, no matter how badly I want them. I acknowledge that, say roger that, you add this up as the trailing sum, and you keep on going about your way. We get to this next unit over. From here, I need to get, we have had 7 so far, I need to now get 93. I need to get 93 from the next 5 elements. 93 over 5, yes, rounded would give us 19. Can I change all these numbers to 19? I'm sorry guys, I really got to take a call. My bad. I'm really sorry about that guys, so I was waiting for this call to come in, so I really had to take it when it came in. But anyways, as I was saying, the number we need from here on in would be a 19. We can't change this number to 19. We know that for sure. So we go on with our lives and we keep on searching. Tomorrow will be a better day, or so we hope. I then get to this number over here. So far I've had my sum so far has been 10. Okay, so I need to get to 100 minus 10, which is 90. I have four numbers that I need to get to 90 with. The closest I could do there, 90 over 4, would be 23, right, when we round it. If I do 23, well, that's not going to help me because I can't change every single one of these numbers to 23. The search continues. We add 12 to the numbers we've seen in our trailing sum. We get to 22. Now, from here on in, we're pointing at this spot now. Our target is 100. We've already seen 22, so we need to get to 78. Okay, we need to get to 78, and we have 3 numbers to get us there. 78 over 3, rounded, would give us 26. Oh, lo and behold, we need all these numbers to be 26. This number is a 30. Since this number, array at I at the index, is greater than the number we need, we're going to return 26 because each of these numbers can and will become 26. So at this point, we're done. We stop off. We return 26 because the number needed is less than or equal to this array at the index I as we're walking through. Right? So this is really the crux of it. We need to A, sort, and then B, keep a sum in this number needed, trailing as we go. And the second we see that our number needed is less than the array at I, we're going to return that number that we need. And that's all there is to it. If we were to hypothetically, let's say, keep filling this array, I just want to show you guys what that would look like. We would get here to 52, and then we'd say, from here on out, we would have, let's see, we need 24 here. This would be 93, and then we'd have 7, and that is the worst 9 I've ever seen. 93, 7, and we need like, I think it's 148 would be our sum, so this wouldn't even make any sense. So really the issue is with these numbers from here on out is let's say I looked at this 7, sure, 7 is smaller than 26, but that means that if we set 7, all these numbers would become 7, right? It's not like just this one will become 7, so that's why it's not an option. I can't leave the rest of these as they are and make the 53 a 7, right? Since these would all become 7, I'd have, 7 times 4 is 28, plus the 10 we have so far is 38, and so you can see we almost like, we're increasing this number needed, and then we decrease down afterwards. And so once we hit this kind of this peak, if you will, that's where we're going to return it, again, based on this condition over here. I think that was a bit of a longer explanation. My computer's starting to heat up, which means it's really been a while and it's not happy with me. But I wanted to make it as thorough as possible because I found at least the logic to be a bit tough to grapple with. With that said, at least the trade-off is the code is going to be super short. I think we got like 7 or 8 lines, and yeah, and that's really it. So let's have a look at the code. We'll figure out we'll figure out how we're going to get it done. We were given an actual array, and the array's already got we've got at least one number in the array. They're all legitimate positive numbers, so we don't need to do any error checking. What we do need to do is take the array and sort it like we said we would. We then said that we're going to need to get some sort of trailing sum going. I'll call it trailing sum. Well, we'll start it at 0 because we haven't started anywhere yet. We haven't added anything in. Then I'm going to say for I in range and the length of the array. So this is the index we're going to be walking through one by one. And we're going to say the following. We're going to say that the sum we need, so sum needed, is going to be equal to, and we had our formula. So we said we're going to need the target minus the trailing sum, so whatever we've had so far, divided by the length, so the length of the array, minus the index, right? So that's what we had up here. So length of the array minus the index, because that's going to tell us how many numbers we have left as we're sequentially kind of getting shorter and shorter. How many numbers do we have left that we can change? The trailing sum will tell us that we have an invariant sum that we've already taken into account, and as we're kind of shortening it, it's more fixed. We only have a smaller amount we can play with. And to get this number, like we said, we're going to round it. So we get actual integers. Once we do this, once we check our sum needed, we decided, or we kind of deduced logically, that if the number we need is smaller than the number we're looking at, then we're going to return smaller than or equal to, the number we're looking at, we're going to return the number needed. So if sum needed is less than array at I, less than or equal to, keep saying less than or equal to, we're going to return sum needed. Otherwise, if we didn't return it, so imagine our first step here, we said we needed 15. We can't do it because it's greater than 2. So then we said, okay, we're going to have to take this 2 as an invariant, and we're going to add it into our trailing sum. So trailing sum plus equals array of. You're recording this now, that final part of the video, I lost the audio for some reason, so I'm just jumping back in real quick to finish this explanation off. After we've done this, actually, this is all we're ever going to do for our for loop. If we don't at any point actually return this sum, that means we've gotten to the end of the array. So imagine here, our t was 1,000 instead of 100, for example. If that was the case, then no matter where we got to, the number we need to fill up this gap to 1,000 would be way more than any number we have here in the array. Meaning that all we could do is return this final element. If that number we needed was, again, greater, it was 100 or 200 or something along those lines, well, that's not the minimum possible answer we can return. By returning the final answer in the array, we're stating that I can't change any of these numbers because this is the biggest number there. And so that's why our final statement here will be, if none of this worked, we're going to return the final number in the array. And I'm going to run this super quickly and press submit now, just to prove to you that it can be done. So you can see it's good runtime, good memory usage, and the complexity, because I know a lot of you told me that to start including that in the video. All we're doing here is we're doing a sort, which will be NlogN time complexity. This walkthrough here of the array is linear, and within this array, the only variables we're keeping track would be the trailing sum, I guess technically the index and the sum needed, all of which are constant memory. So it would be O of NlogN time, O of 1 space, super efficient. And yeah, I hope you guys enjoyed. I hope you learned something. This was again, it was a bit of a tough one for me to grapple with. So if you were struggling with it, I hope this eases the pain at least a bit. As always, let me know if you have any feedback down below, questions, comments, concerns, like, comment, subscribe, share. I always trip over that part, all that fun stuff. And as always, I'll see you guys in the next video. Peace.